Chicago. Alright, so it says given x squared over x squared minus 1, tell the intervals on which it's increasing and the intervals on which it's decreasing. And I believe there were some like this on the homework. What's tricky about this is that this graph is not continuous the whole time, so you have to skip over where there's not a point. But if I started here at negative infinity, what's happening with the graph right here? Is it increasing or decreasing? It's increasing, right? So I'm going to say it's increasing from negative infinity to where does it stop on the x-axis? When I'm talking about increasing and decreasing, I'm talking about the interval on the x-axis, not about what the y is. So, like, this stops because there's an asymptote here, right? How would I know, besides just looking at the graph, how could I confirm where that asymptote is? What x can't be in the denominator results in where my asymptotes are on my graph. Right? There's a direct correlation between my asymptotes and which values are excluded in my domain. So if I set this bottom equal to 0, I would get x squared equals 1, x equals plus or minus 1 should be where my asymptotes are. So at negative 1, it's never going to get to negative 1, so it's increasing up to negative 1, parenthesis or bracket? Parenthesis, because there's an asymptote, right? Like it's not defined at negative 1. On our notes yesterday, we had those brackets because those were defined at that point. But because it's an asymptote, it has to be a parenthesis. And then if I skip right over negative 1, and I go right on the other side of negative 1, what's happening with this graph right here? It increases until when? So I think it's still increasing. So I'm going to put it's increasing. I'm going to put union. It's still increasing right on the other side of negative 1. And Sean, what did you say that I'm increasing till? 0. Should 0 be included or not included? Like, should it be a bracket here or a parenthesis?
Bracket.
Why would the book put a bracket here and put a parenthesis on the negative 1? Yeah, there's an asymptote here. This is where we talked about in here yesterday. The book puts a bracket there, and I said that I think sometimes I want to put a parenthesis, Tyler, because I want to say it's doing nothing at 0. It's not increasing or decreasing. But the book puts a bracket there. So probably if you want to get your answers out of homework, if it's included in the domain, you would put a bracket. But that's a hard one for me because if I switch now to a different color, right, here starting at 0 again, what's happening with my graph? It's now decreasing. And so the reason that I struggle with the bracket is because if I say bracket 0 to whatever I'm going to put here, it's hard for me to have a bracket on both sides. Like how is it increasing at 0 and decreasing? So that's where I think a parenthesis is okay. And it's this big whole debate in math among nerdy math people debating about whether there should be brackets or parentheses. But this book says brackets, so we're just going with it. In AP Calculus, on the test, they do not mark you wrong if on intervals like this, whether you put a bracket or a parenthesis, they count both correct because there's a big debate among them. Only math people can get into debates about things that no one else can care about. Do I put infinity right here? No, because so I have to skip over that part because it's not doing anything at 1. And am I going to put a bracket or a parenthesis? And then what's happening with this part of the graph? Also decreasing from 1 to... And again, I'm assuming that this is going on forever, even though the window just shows so much, right? Because I know it goes on, so that's why I'm doing infinity and parenthesis on it. So intervals of increasing and decreasing, kind of a little extra practice with your interval notation. The only other thing that we didn't talk about yesterday was absolute and relative maximums. So I just said relative, but local is another word to use, so I'm going to write relative up here as well. So last year when you talked about max and mins in Algebra 2, most of the time you were talking about those turning points, which are local or relative maximum and minimum values. So a local maximum is just a high point on the graph, right? So like I'm going to draw a graph like this. So a local maximum would be a point where your graph changes from increasing to decreasing, and there's that high point before it turns down again. So we can say it's where the graph changes from increasing to decreasing. And the reason it's called a local maximum is it may not be the exact highest point in the graph, it's just the highest point in that part of the graph. But if they ask you for the absolute maximum, it is the highest point on the graph. Do all graphs have an absolute maximum? Give me an example of one that doesn't. A straight line doesn't. A parabola that opens up doesn't, right? Like, it goes up forever, so there is no highest point. So not all graphs have a maximum, absolute maximum. Not all graphs have even a, well, I don't know. Most graphs have at least a local, right? I mean, we could argue straight line at the whole graph's a maximum, I don't know. So if it doesn't change, we could say it doesn't change. So local minimum is the same idea. Local minimum is a low point on the graph. Sometimes people call like maximums peaks and minimum valleys, but peaks and valleys, there you go. So a low point is where your graph changes from decreasing to increasing. And basically, again, that's because it's like the lowest point in that part of the graph. So this would be a relative min, and this would be a relative max. There's totally not enough room to see that, but that's good. It changes from decreasing to increasing. And again, your graph could have more than one local minimum. It doesn't have to be the lowest part on the graph. But if they ask you for the absolute minimum, it is the lowest point on that graph. And again, not all graphs have an absolute minimum. Sometimes the absolute minimum and the local minimum could be the same thing. But it's just kind of an important idea to talk about whether or not it is just a local extrema point or a absolute extrema point. So we say extreme points because they're highs and lows. Plural of extreme, extrema, if you didn't know that. And there's some good vocab for that. Extrema. Local extrema. I know, right? Okay. So that's the only thing I didn't get to yesterday. I don't even think I have an example of that, right? So I want to do more notes today. It's just never ending. I think that's good. Probably that. I think we just combined two. Do Gaffigan and Gallagher's got the bus. That guy? I don't know that guy. He's really old. See, when I was a kid, they had these specials, Gallagher specials, and he was median, but at the end of his show, he smashed a lot of food and watermelons, and like people would like wear like ponchos and trash bags to this thing because like you just have like watermelons all over the look it up. Not right now. Later. Okay, so telling whether a graph is symmetric about the x-axis, the y-axis, or the origin can help you when you're graphing, and also it leads to even and odd functions. So that might be as far as we get today, and then we'll save asymptotes and graphing until Monday. But graphically, way back in geometry, who did you guys have for geometry? Stuart.
No.
Why what? Hopefully, maybe you talked about symmetry, or maybe in middle school you talked about symmetry. That it just would be, if it's symmetric with the x-axis, it means you can flip it over the x-axis, right? So it looks the same, but you flip it over, so it would be like this, right? Roughly speaking. What if I can, what if I can do this? Oh, but it just looks the same thing. I'll just. The big thing I want you to know is what happens to the point. When you flip it over the x-axis, one of them changes, one of them stays the same. And I don't feel like you have to memorize that, because if you just think about what happens when you flip it, you're like, oh, the y changes, the x doesn't. So down here we can say, if it's symmetric with the x-axis, then every point that's on it, then also x negative y will be on that graph. I don't feel like anybody does the little quotation marks anymore. Y-axis symmetry. You're flipping it over the y-axis, so this would become like this. And what happens to that xy point? Right. So it's negative x, positive y. So if it's symmetric with the y-axis, if xy is on the graph, so is the point negative x. So on the origin takes it and flips it over the origin. And so that's the one that I'm not a very visual person, so it's always the hardest for me to visualize. But it kind of looks like this, right? Like it takes that and flips it over that way. Someone made a comparison once, I never thought about it, that origin symmetry is like flipping it over the x-axis and then the y-axis, or the y-axis and then the x-axis. And I was like, I never thought about that before, but it's totally true. And that's why if you do both flips, what happens at this point over here is they're both negative. Thinking about our talk about functions, can a function with can an equation with origin symmetry still be a function? Can an equation with y-axis symmetry still be a function? Can an equation with that does not pass the vertical line test. But we don't see a lot of x-axis symmetry because most of what we deal with are functions. And so we don't see a lot of that. Okay? So part of your homework asks you to find out whether they're symmetric or not. And it says use algebraic tests, which means that they don't want you just graphing on the calculator to see. They want you to think about the rules. And you can kind of tell sometimes without doing a lot of work, but I'm going to show you. Okay? Experiment by rule. I want to check, does this have x-axis symmetry, y-axis symmetry, origin symmetry? Mostly you want to think about what are the rules, what changes. And if it has that symmetry, when you do the change, you can, let me just, so what was this? xy changes to x negative y. This one was xy changes to negative xy. And this one was xy changes to negative x, negative y. What it means if it's symmetric is if you do the change, like if you plug in x for x and you plug in negative y for y, you can simplify that and get back to the original equation. That means it's symmetric. So a lot of times you can tell by just looking, and I'm okay with that, but I just want you to know where it comes from. So if I was going to check x-axis symmetry, I'm going to take, and x isn't going to change because x stays the same, but I have to replace y with negative y, so that becomes minus negative y equals 0. Is this equation the same as the original equation? So that means this is not symmetric with the x-axis. on this one, if I replace x with negative x, I'm going to try my work here, negative x squared, and y doesn't change, does that simplify down to give me back the original question, the original problem? Because negative x squared is still just x squared. So people realize pretty quickly, oh, if it's an even exponent and I plug in a negative, it's going to stay the same. If it's an odd exponent, it's not. So this one, it is symmetric with the y-axis because this looks like this. So if you can tell by just looking, and sometimes, especially if we have it too, if I make x negative and y negative, is that going to work? No, because the x would stay the same, but the y wouldn't. So this is an example that it's only symmetric with the y-axis. You could just say y-axis, you could say the no, yes, no, however you want to do it. I think on homework you have to choose which one it is. Most of the things we do right now are going to be symmetric with one or the other, but there are examples. Can you think of a shape on a graph that could be symmetric, like all the x-axis, the y-axis, and the origin? A circle, and it would have to be centered at the origin. Let me draw a careful circle. Because it would be symmetric with all of them. And then next semester, when we do conic sections, we're going to do a lot of non-functions. We're going to even graph stuff like this, like a, how about this? Oh, that's terrible. They're supposed to all be the same length. And they're symmetric about a lot of them as well. It's called a rose curve, even though it doesn't look like a rose, but it does look like a flower. We'll do that next semester. I know you're really excited. You did drop today, I'll break it up. I don't hold trouble. I'm not going to beg you to sit.
You're not allowed to stay in class.
Remember that you get college credit for this class, so that's the motivation. Most semesters, this is one semester college credit, next semester is one semester college credit. If you qualified to sign up for dual credit last year, then you already have qualified to sign up for dual credit this year. I think. Maybe not. Did you not do dual credit English last year and listen to law? Oh, we'll have to sign you up. I'm waiting on the item check lady. I don't know. It always takes forever. But basically, this semester is Math 136, which is college algebra, and next semester is Math 137, which is analytic algebra trig. That's 6 credit hours in math. And if you can get a C or better in this class, then you can get college credit. If you get below a C, I'm going to drop you to the college credit class because I don't want you to but we'll talk more about it as I get more information. And then maybe you have to take a test, have a certain PSAT score or SAT score. So I kind of forget. But most people last year, and you can take the test like 3 times. Kind of like our homework. You can do it 3 times. So we'll talk more about it as I get more information. But just know, Justin, that's one reason you shouldn't drop my class. Because a lot of people that take this as dual credit, if they're going into a field that doesn't require them to take much math, they don't have to take any math in college. Computer science, you're going to have to take more math. But that's okay. AP Calculus, you also can get college credit for if you're a junior and plan on taking AP Calculus. Okay, even functions. You know what an even function is? If it's even, that means it's symmetric with the y-axis. So what's a good example of an equation that's symmetric with the y-axis? Yes. But just y equals x squared. Good old basic quadratic, right? What makes it symmetric with the y-axis, so another way of writing symmetric with the y-axis is we can say when you plug in a negative, you get the same thing as when you plug in a positive, which is the same thing around. But we can say f of negative x equals f of x. And x squared, for every negative number you plug in, you get the same thing when you plug in a positive. And then we also have odd functions. An odd function is symmetric with the origin. Look at that fancy font. That's okay. It's just your notes. So remember, the origin is when it flips from like quadrant 1 down to quadrant 3. So that's when both of them change sign. So that means if you plug in a negative x, the whole function becomes negative. So we say f of negative x equals negative f of x. What do you think a good example of an odd function is? So I'm going to give you a hint. An even function, what do you notice about this exponent right here? Y equals x cubed is a good go-to example of an odd function. Do you know what x cubed looks like? Just x cubed if there's nothing else. It's just this little s kind of thing, where this side just goes positive. This is exactly the same except for it's negative. So at 1 you get 1, at 2 you get 8, at negative 1 you get negative 1, at negative 2 you get negative 8. Right? So it's an odd function. So again, why is it important to know even odd functions? Could you survive your life without knowing about even odd functions? You could. But if you're graphing without a calculator, if you recognize that something's an even or odd function, like even function, if you graphed half of it and you know it's even, you know the other half is exactly the same. So like you have to work. If you know it's an odd function and you graph half of it, you know the other half is exactly the same, just down going negative. And so it's supposed to be a helpful way of graphing. Or you could just teach you. Here's what you have to do, and I promise this is it. My last slide, I'm not going further. You have to tell me, is it even, is it odd, or is it neither? Because not every function is even, right? That's symmetric with the y-axis. Odd is symmetric with the origin. Sometimes it's not symmetric with either, so that would say neither. It shouldn't be that you're just guessing here. It should be that you're going to, for each one of these, you're going to plug in negative x for x. And what you're trying to see is if I get back exactly what I started with, that's an even function. If I plug in negative x and I get back exactly the opposite, so I can pull a negative out of everything, that's an odd function. So I kind of put these in the wrong order because I feel like number 2 is the hardest. So we're gonna start here and go backwards. Okay. So I'm gonna start with number 4. We did number 1 already, didn't we? Here's number 1. Boys. Monday. See, this is why I'm doing my other classes today. I made you receive charts. I'm going to post it. Monday, I'm going to be moving my post. No, I just switched. We don't even know how long I spent making up this little fun way to make a new screen chart last night. I made up all these equations. We each have specific answers, and then I'm going to get them all in note cards, and then solve their equation, and then ask them what row they go in.
For us.
No, it's equation. So we just did an equation, we just solved equations. But like I decided, like this row has x equals negative 1/5, and this row has x equals 4, and this is x equals negative 2. So like I started with the answers, and then I had to come up with the equations. And it took me like an hour and a half to come up with all these equations. And then I got scared I was wrong, so I went to a little teeny website where you just type in your equation and the answer. I know you know about it. And
I already know.
I know, and if you block one, there's 12 others in place of it. That's why homework doesn't count. And, like, I'm aware that you can cheat if you like. And so I went to a website, and I typed in all my equations, and 5 of them were wrong. So then I had to go back and my wrong equation. So after spending an hour, then I checked them, and then these were wrong equations, and I had to come up with new equations. I was like, this is ridiculous, but I already put an hour of my life in it. Could have quit. I could have quit, right?
I was like, that's what
And here I'll just be like, Justin, you sit in this corner. Sean, you sit in this corner. Everyone else sit wherever you want. I'm just kidding. Just kidding. Okay, so again, it's kind of up to you and how much work you show on this. But what I'm trying to do is determine when I plug in negative x in here, is it going to stay the same or is it going to change? When I plug in negative x into the fourth power and a negative x into the squared power, and I can't plug in negative x into 2 because it's not an x. You have an even exponent, it's going to stay the same, yes? So this is going to be x to the fourth plus x squared plus 2. So since every part of that stayed exactly the same, I can say that I know number 4 is even. What about on this one? If I plug in negative x in here, the x squared is going to stay the same. What happens to the 2x? Because 2 times negative x would be negative 2x, and then the 3 has to stay the same also. So this is definitely not even because it did not stay the same, yes? If it's odd, every single thing had to change signs. Did everything change signs? No. So this is an example of neither, because it didn't all stay the same, it didn't all change. So this is neither. British people say neither. Okay, so now this one is the tricky one, I think, and it's because it's a square root. But if I plug a negative x in here, this would become negative x, and on this multiplied by, that would stay the same in there, right? 1 minus x squared. Because when I square it, it would still be positive, and then literally would still be the minus sign in front because it's a square. If that was an odd exponent, that would have changed the plus sign. What do you mean it might change?
Well, like, so it's going to be the same.
Yeah, and I'm totally okay if you are, like, when it's an even exponent, if you just leave it the same because you know it's even. Like, down here, I, like, showed the step and then I wrote it. Here, I just said that one stays the same. So it's up to you on how much work you show to help yourself. So now here's the question on this. Did this change so it's odd, or do you think it's in between and it's even? I heard, that's what it sounds like. I think it's neither. I'm just kidding. I think it's odd, but people usually argue with me that it's neither because this changed and this didn't change. Do you feel that way? But because it's multiplication, right? Think about if you had like 3x, I'm just going to make a terrible problem here. 3xyz, how do you even graph that? I don't know. You can't, but. If you plugged a negative in here, negative 3xyz, just pretend one of those was negative, you could factor the negative out because it's all multiplication. Like, it's not like addition and subtraction. Whereas if you had negative 3 plus x and you factored a negative out, it changes the sign in the middle because it's addition. You see the difference between this and this? Like, if you factor a negative out of multiplication, you just pull the one negative out, nothing else changes. But if you factor a negative out of addition, it's like the distributive property, and you have to change the sign of everything. So the reason that this works is I could factor that negative out front, and it just pulls that negative. This is multiplication, so it doesn't change anything in the square root, because it's just multiplied. Multiplied. Even though there's addition under there, it doesn't matter, it's multiplied. So this is saying I can pull the negative out, everything else stays the same after I pull the negative out, so that's why it's an odd. Sometimes those are a little tricky. Shouldn't be too bad, but I think that's a really hard example to change it. So the other thing that's in this section that I'm going to just stop with today and let you finish your homework from yesterday if you still have it, or start on your homework from today, is talking about asymptotes and how to find vertical asymptotes and horizontal asymptotes. So that means that the homework I put online for day 2, you also are not going to be able to finish. unless you just try it. So let's look there real quick. Day 2. There are only 5 questions on this one, and we didn't even talk about them all yet. So like even, odd, or neither, you could do that one. Symmetry of the graph, even, odd, or neither. This is those only the first 2. The rest of these are talking about asymptotes, and we'll just pick up there on Monday. So you need to finish 1, 2, day 1, and on that last example from 1, 2, day 1. Question 11 says, using a graphing calculator, find a local max and a local min. If you go to desmos.com/calculator, you can type that equation in there, and you should be able to just touch where the maximums are, like it'll give you the maximum. There's also ways to do it on the graph calculator that you can do the intervals like we did with that. This is not the one that's on the homework, but notice I graphed it, and it automatically put this point here that I can touch right there, and it gives me that local minimum value. And if I scroll up, it gives me that local maximum value without you having to do a lot of work. So desmos.com/calculator. I'm pretty sure that's one of the on our classroom page that we about how to link. But this is a really good site to bookmark or to have it somewhere that if you need a graph calculator, if you don't even have to solve it with X. Like you don't even have a Y over there with it, and it's rather good. It's really easy. It's really nice. Alright, so definitely check that one out as you're doing that. Try to finish 1, 2, day 1. And a couple questions on day 2, and on Monday we'll talk about asymptotic graphing, and I have a worksheet over graphing, so I don't know. We'll see if we do that Monday or if we just wait for that. Again, see me if you have questions still over your test sections, and don't forget about the when they're talking about maximums and minimums, the highest point is the y value, not the x value. And if they ask for the maximum or the minimum, They're just wanting your y value, not like the whole point, not the x value, unless it says where does the maximum occur, that's the x value. So it's kind of just getting the practice. Local is just the turning point.